What is a shape of constant width? Well, here are three shapes you are undoubtedly familiar with. Only one of them is the same width no matter how it is rotated, that being the circle. The triangle is shorter than it is wide, and the square is longer along its diagonal. Besides the circle, though, there are actually infinitely many other shapes of constant width, the best known and most useful of which is called the rolo triangle. So you can make one of these by centering three circles at the vertices of an equilateral triangle. You get a shape whose width is constant. You can see the width is the length of the side of the triangle. It's also the radii of those circles. This shape is named after Franz Rolo, a 19th century German mechanical engineer who didn't discover it by any means, but he worked extensively with it. We will get back to him. Similarly, you can construct a shape of constant width out of any odd-sided regular polygon by turning each side into an arc with its center point on the opposite vertex. Now, it may be obvious to some of you that you can't make one with an even-sided polygon like a square. If you imagine trying to, you can see quickly it doesn't work. It just turns into a circle. So shapes of constant width can be used to make, for instance, the cover of a hole you don't want to drop said cover down, because whichever way they are oriented, they are as wide as the hole. So most manhole covers are circles, partly because the pipes they're on top of are also circular, but you could make them rolo triangles. Just don't make them actual triangles like Nashua, New Hampshire did for some reason. So since a rolo triangle is the same width no matter how it is rotated, you can use it as a wheel. Here are three triangular cylinders connected together under a plate. As those cylinders roll, that plate will move completely horizontally with no bumps, no vertical displacement. It is hard to believe without seeing it for yourself, so if you ever get a chance to play with these, I highly recommend it. Is a rolo triangle wheel a practical idea? No, definitely not. Though the height of the wheel never changes, the height of the center of the wheel does. As this triangle rotates, the center will move in that circle indicated there. A regular vehicle attached to the center of a wheel via an axle will bounce up and down terribly, even if the wheel doesn't. So to fix that, a hypothetical bicycle, for example, would have to rest on platforms on the top surfaces of the wheels. The bicycle's front fork would need supercharged shock absorbers, and the back fork would need to pivot to adjust to the changing height of the center of the wheels. But again, the platforms and the rider would not bounce. They would not be displaced at all. So hypothetically, it would be a very rideable bike. A hypothetical rolo-wheeled bike would only be limited by the friction between the wheels and the platforms. As a side note, a wheel with reduced friction makes for a pretty poor wheel. But you can see the bicycle on the right has two different rolo polygons for wheels, and the picture on the left, if you couldn't guess, was taken at Burning Man. So going back to this previous diagram, if you notice the thick outline, that is the shape that is swept out by a rolo triangle rotating in a square. As it rotates, in fact, it's always in contact with all four sides of the square, remember that, and sweeps out almost all of the square, remember that, only leaving those curved corners, which brings us to the first really useful application of a rolo triangle, drilling square holes. With a square jig, a rolo triangle-shaped bit, and an articulated bit holder to accommodate the moving center of the bit, you can drill an almost perfectly square hole, leaving just the corners to be chiseled out. The way the rolo triangle interacts with a straight surface really unlocks its practical potential. It is excellent at converting rotary motion into intermittent linear motion. Here, it is rotating about one of its vertices inside a rectangular frame that can slide back and forth. As the triangle rotates from position 1 to position 2, the frame slides to the right. However, as it rotates from 2 to 3, the frame doesn't move. 3 to 4, the frame slides back to the left. 4 to 1, again, the frame is motionless. If you use a square frame, as the triangle rotates about its vertex, the frame moves right, then down, then left, then up. And thus you have converted rotary motion into intermittent linear motion. This transformation of motion is what Franz Rolo was so interested in and what he pioneered, particularly with the help of this shape. That's why it's named after him. Here is a practical use of the intermittent motion. It's a Soviet-designed 8mm film projector. The mechanism advances the film up one cell, then pulls back, resets, and moves in again. Other projector designs use different intermittent mechanisms like the Geneva drive. So besides translating motion, here are a couple other very nifty applications of shapes of constant width. First, vending machines, which work partly by measuring the width of the coin inserted. You couldn't use a perfectly square or triangular coin. They would give different measurements depending on their orientation, and the vending machine couldn't identify them. However, a coin of constant width, like each of these are, can be identified by a vending machine. It can also be easily identified by your fingers in your pockets. The Wankel rotary engine uses a rolo triangle cylinder, albeit with a slightly flattened sides, and takes advantage of the triangle's ability to sweep out a space, remember? It segments the engine housing into 3 distinct cavities, you can see there, which are all simultaneously involved in different strokes of the same 4-stroke cycle that you might be familiar with if you know how piston engines work. So ironically, the piston engine here is the one transforming the up and down reciprocating motion into rotational motion. The Wankel engine doesn't need to. The advantages of the Wankel rotary engine include a high power to weight ratio and very few moving components compared to piston engines. This makes them most useful in vehicles that need very small engines. Wankel engines are not that common in cars. The most well-known model that used them was the Mazda RX series. They are not very fuel efficient, and they're pretty dirty because they burn a lot of oil. Part of the reason for that is that it's difficult to seal the sides of the rotor, particularly the non-triangle sides. So if we move into 3 dimensions, if we make the analogous changes to a tetrahedron that we did to a triangle, we get the rolo tetrahedron. Now, this shape is actually not one of constant width. You have to round 3 of the 6 edges to form a Meissner tetrahedron to get a solid of constant width. But you can also just rotate rolo polygons about an axis to create other solids of constant width. So here next to the sphere, you have a rotated rolo triangle, pentagon, and heptagon. These are all solids of constant width, which means similarly to the rolo triangle wheels, these could be used, for instance, as ball bearings that won't roll away. Unfortunately, there is not much other practical use for solids of constant width. So finally, I'll leave you with 2 other examples of a rolo triangle in everyday life. I highly recommend that you find video of rolo triangles in action, interacting with straight surfaces, because they are quite something to behold. Thank you to Mike for hosting this event. Thank you to all the other presenters. You were awesome. And thank you to everyone for listening to Math.